Welcome everybody. It is a pleasure to have Alexis today, Alexis Vasseur from UT Austin, and he will talk about stability of discontinuous solutions for inviscid compressible flows.
Thank you. Thank you for the introduction. Thank you for the invitation. And yes, so I will talk about this kind of thing. So this is actually a line of work that I've developed for quite some time, but I think we have now really some very exciting result to present. So, and I will put it into a very strange limbo, and I will explain what I mean by this, but it will be about a contraction with shift. But it's really about what Camille just said, right? I mean, it's just that I'm trying to advertise a certain strange way to present these things. And actually what I plan today is to give a sort of overview of several directions we're going. And because of that, I will present actually three different results, which have a slightly different perspective, but in some way really fit all in this line of work. Well, maybe I will not have that much time to explain, but I will try to give at least a very rudimentary idea behind this. So the first one, for the first one, it will be 1D, right? So I will consider, so first, I will give one example in multi-D, but let's begin the first 1D. And I could, to try to avoid making a list of weird-looking assumptions, I will just focus on one example. We can do more, but I think that that would be fine, and that way will save me a lot of headache writing things in details. And let's consider the Euler with the gamma law, right? So I just consider, so it's 1D, so it will be dt rho plus dx of rho u is equal to 0, and dt rho u plus dx of rho u squared plus rho gamma is equal to 0. So this is your simple Euler gamma law system. It includes especially the shallow water equation if you take gamma equal 2. And of course, if we want to consider stability problem, it's very well known for a very long time that you need, I mean, maybe not enough, but you need at least to consider a solution which decrease the entropy, right? So we'll consider, so it will be my system 1, and we'll consider only solution which verifies dt eta plus dx q negative is my 2, with in this specific example, so which is important is that the entropy is convex with respect to the conservative quantity, rho and rho u, but in this context, let me just write what it is, right? It is kinetic energy, actually the physical energy, we call it entropy, mathematical entropy, so this is rho u squared over 2 plus the rho gamma over gamma minus 1, and then you have the q, which I can write, I'm not sure it's really relevant here, but let's write it down, and it works with eta plus rho gamma u. That's one way to write it down. Okay, so that's it. That's what we consider. And in order to explain a bit what I'm doing, I should do a very brief review of what was done since very long time. So especially one very nice framework to work on this equation is to consider the small BV framework. Right? And well, in these things, so it's basically you want to have a small BV as initial value. You construct a global solution, which is still small BVs. It's been done by Glim a long time ago. So this is 65, really a long time ago, so it's existence. Interesting enough is that here we want to talk about stability. The stability came really a long time later, and it was due to a series of work of Bressan, so I should say Bressan and al. Actually, and but all around 2000. It began actually slightly before. The latest version was slightly after, right? And it was about uniqueness. And since I will really relies on what was done there, let me write exactly what the result is. So this is uniqueness of the BV solution in the class of BV solution, right? So let's write the class, I will call it SBV, right? And this is considering all the U, L infinity in time, BV in X, should write small bv. And well, it's not really, really important, but it's interesting for us, is at the time, it needed an extra condition that was called BV condition along space-like curve. Space-like curve. And I will explain what it is only if you ask me, otherwise, I will just say it's a pesky condition that it's okay. I mean, it's completely okay working with that because actually all the solutions they constructed, whether the solution actually constructed by Gleam originally or through other numerical scheme or via the inviscid limit of what they call the artificial inviscid limit in 2005, all those things verify those conditions, right? But I think that it seems even at the time that this condition shouldn't be required. But nobody was able to get rid of this. Okay.
And just to make sure, BV stands for bounded variation?
Bounded variation, exactly. So that's why you can have, especially you can have shocks, right? I mean, this is discontinuous. It actually considers discontinuous solution, but even in more general situation, right? Exactly.
Okay,
yes.
Thank you.
Sorry, can you specify more about this small BV condition along the space?
Maybe we should keep it for, I mean, okay, I can. So basically is to say that on top of being BV, well, BV, right, it seems to be very minor, but so being BV means, so this is time, this is position, right? So what they say is that for any time, if you take a slice of time here, this is BV in this X. What they needed on top of it is that it's not BV only on those lines, but it's BV also on curve, which are very flat, right? So it's slightly more, right? It's a BV on things which are not flat. Well, it just shows the technicality of working even on those BV things, right? I mean, but this was just a technical thing that they need, and it's closely related to the finite speed of propagation. Actually, I mean, you can see that results in this area are pretty slow, right? I mean, existence 65, uniqueness in 2000, with 2020, and basically the only thing that I can say before what we've done doing on uniqueness. But we are not working with Navier-Stokes, we're not working with incompressible model. We are working with model with finite speed of propagation, right? So it takes time, right? Finite speed of propagation.
Thank you.
It was a good joke, sorry.
Sorry, Alexis, to interrupt you as well, but don't they need also some, I mean, I remember reading actually the proof by Alberto, he needs the semi-group property, right? So it does.
The what property?
The semi-group property, or do you mean for?
Yeah, so this was before. So the first result was a semi-group property, and then they tried to relax it, right? And in some ways, this was the more relaxed one. So actually, there was several, right? I just picked one, but there was another one which was mean oscillation, whatever. But in some way, I think it's the best one that they have. But this was really this. It was in order to put it in the framework and say, oh, this is the same as the one that you have by using the semi-group. Exactly, it was linked to this. Okay, and but on this specific example of the system that I gave you, there's another theory, I mean, family of theory, which was done and was really L infinity, right? No smallest condition, and it's everything which was done with compactness, compensated compactness, right? So it's also something pretty compactness, things pretty old. I mean, I should cite Tartar, right? I mean, this is the 90s. And Guixiang Chen then work with this, and Lyons, Pertam Tanman with the kinetic, and a lot of other people, right? But here, there is absolutely no result of uniqueness, nothing, absolutely nothing in this situation. And so there is a gap, because even with, if you have solution which are BV, right? I mean, what can you say? Are those solutions, they're unique in terms of among the BV solution, but are they unique in terms of L infinity function? That's something that there was no clue. And this is in this direction that we wanted to go. And the first result that I wanted to give here, which is actually one of our latest results in this area. So consider another set of solution, S, and I will call it S weak. And this is all solutions, so you consider all U L infinity R plus R, a weak solution to 1, 2. So the equation plus the entropy. And here again, we need a condition, a weak condition, weaker than BV, far weaker than BV. This is a strong trace property. Let me put it here. Okay. So, so let me maybe say a word about this condition. So this condition, which comes quite naturally, I work on this 20 years ago, even, yeah, something like that, which was not connected at all to this work. The problem is that it's not really well known which solution here have this solution. But again, in one, if I'm trying to do it in one picture, what it means is that for any nice curve, again, so this is xt, right? So this is a curve x of t, Lipschitz, right? Then your solution, you can give a notion of limits when you go to the curve u plus and on the left and on the right, right? And so this means that you can define u of t at x of t plus, this would be the u plus, and u of t x of t minus, and will be the u minus, and you can have it in L2 strong. This means that if you, the thing that you cannot have is a solution which, when you get close, oscillates a lot in time when you are closer and closer and closer to your line. So this is something that you should relate to, because this is in multi-D, this is a telltale of convex integration, right? I mean, usually when you convex integrate, you have this kind of property. You have trace, that's fine, but usually things oscillate a lot, you lose the thing. So this is typically what I don't have, right? So what I try to avoid. Along this condition, and only this condition, then we have the result. Let me put here, so here I am. So I should say this is with gang chain. So from University of Kansas, Sam Krupa, who was a former student of mine, who is now a postdoc in Leipzig at the Max Planck Institute, and myself. So this is available on archive. So it's really 20. And here it is. So you consider a solution. So let's call it U. So you consider U a BV solution, small BV solution. Let me put small BV solution. Right. So with initial value U0. So U0, so this thing is small bv. And now you want to have a perturbation of this with a function which is just in S weak. So you consider actually a family. So now you can say U epsilon, a family of solution which are all S weak. So they are infinity both with this strong trace property and with initial value U0 epsilon. And what I claim is that if U epsilon 0 converge strongly in L2 to U0, so this is for the initial, then your U epsilon converge strongly in L2 to your U. So it's stability with respect to the initial value, stability of the BV solution, but among far weaker solution, right? So in some way, I mean, you will see that actually it's related to the work of Dafermos and Diperna, right? In some way, the same way that you can talk about a weak, strong solution for a weak, strong principle, right? For smooth solution, here it is a weak BV principle, right? Stability result. So that's the way we frame it, right? Another remark is that actually, because this S weak contains SBV, actually just BV solution. If you have BV, you are in S weak. This means that actually it removes the condition, the strange condition. I forgot even of BV along condition along space-like curve, right? So this removes the condition. Let me put it in yellow. The condition of Bressan, and actually, I think it's really the first improvement of a uniqueness result in this direction since 2000, right? I mean, this is really the first thing in this direction. And what I would like to say,
so maybe you're not assuming on the solution U when you say small BV, you're just assuming that it has small BV norm, right? Nothing else.
BV variation, exactly.
So you're not assuming, not even for the final guy, you're assuming the thing on the space-like curves.
No.
Am I correct?
Exactly. So we don't need it on the initial value, and I mean, no, nothing. Now, I mean, this is really a uniqueness group.
So when you say small BV, it's just a bound on how big is the total variation.
Exactly. It means that the result, I mean, the result works like they exist, I mean, for any system, any point in the domain, then there is a small ball, a TV small, such that when you are close to this, I mean, it's a sort of perturbation of constant, if you want, in BV. That's it. But now you have uniqueness in a large set where there is no smallness. That's the main thing. So I don't know. Yeah, times goes pretty far. So I would just say just one quick word, but I would like to go to the next work. So.
Sorry, could I ask just a general question about these systems? So
yes.
Can you, in simple cases, can you describe the shocks? I mean, is this what you're trying to do, right?
Exactly. So, well, when you have a single shock, and actually that's a good remark. So if you consider even a single shock, so what is a single shock situation, right? And even for small shock means that you on top of it put an assumption that the shock is not very big. So what is that? This is spatial traveling waves, right? And this is solution which are exactly like this. So here is in X, right? I represent in X. So you have a certain value. So you have a speed here, so sigma t, so a certain time t. So it's a traveling wave. So it goes, you know, at speed sigma, right? And you have a solution which is constant on the left and constant on the right. Mm-hmm. Right. So here I do, of course, a scalar thing. It's not scalar, right? So your UL has two value, rho L, UL, and UR. So I will be big U to talk about the solution, right? So solution on the left and solution on the right. and this is rho r u r, right? So this is kind of situation, and basically, in order to be a solution, what you need is to find the Rankine-Hugoniot conditions, a condition which link UL, UR, and sigma, and this is some algebraic condition, right? Which
this is equivalent to the entropy, or
well, no, you need the entropy on top of it. This is equivalent to the equation.
Okay.
One way to see it is if you, I mean, let me just show you a very simple example just to have an idea, right? So if you consider burgers, so burgers is even simpler, is ETU plus
that's what I'm familiar with.
Exactly. So let's put burgers, right? Anyway, it's a good example. And let's say that you try to find this kind of waves with sigma equal to 0, right? So a steady wave, right? If you want a steady wave, then what you want is to have the xu squared is equal to 0.
Yeah.
So it means that u squared cannot change. So you have a solution for this, actually two, is putting 1 and minus 1.
Sure.
And that will be 1 here and minus 1. And that's shockwave. So you see, this is the equation which gives the condition for it. Now the entropy says that because you could put 1 and minus 1 and 1 and minus 1 and, or the opposite, right? And there's only one which is entropic, and the entropy say, well, you cannot put 1 minus 1 1. This one has a smooth solution, a Lipschitz solution. So this gives you how you have to order the 1 and the minus 1, and that's what the entropy condition gives on top of it.
Okay. So
but this is a typical situation here.
So I know that you can often just put in you know, a viscosity term, a higher order viscosity term, and then let that go to 0, and that should do the same thing.
Yeah, I will
Is there
talk about
something
that.
analogous here?
Yeah, I will talk about that. I will talk about that actually very, very soon. Actually, maybe it's the right time. Maybe it's the right time. Let's talk about that. So actually, for its single shock here, right? I mean, it's still unknown if you have if it is, as I said, unique in this space of only weak solution. With strong traces, okay. Well, there is other way, and you just mentioned it, to get the right solution, at least in spirit, is to say, well, let's try only solution which came from physics, because this means that comes from a viscous model, the Navier-Stokes, right? And that was the next thing that we did actually, is that if you take limit and Navier-Stokes, then you don't need this additional condition. And this is other line of work. So maybe I should put here. So now we consider Navier-Stokes. Actually, in this situation, we look at the Lagrange situation. I don't know if you want the equation. I can give it. I mean, it's not that complicated. So if you look at the Lagrange frame, then actually this is a P system, so it's even simpler. V is 1 over rho. The value of the equation is very important, but that's what we have. So this is the equation of the rho, which becomes like this. And you have the equation on the U, which becomes, so rho gamma, let me put the pressure of V. And you have the Navier-Stokes here. So this is the Navier-Stokes. Thanks. And I put a nu here, I put it in yellow, right? So this nu will be considered very small. And basically now what I want is consider, well, if we consider even a weaker set, so what is now my weaker set of solution is they are not solution anymore. So what I want to consider now is a set of what I will call inviscid. And this is things which may not be solution of the wiki of the limit nu equal to 0, but this is any things, any u which are limit, inviscid limit, nu converge to 0, inviscid limit, weak inviscid limit, nu converging to 0 of solution to, let me call it 3. Right, so formally, if you take nu converge to 0, you converge to, I mean, Euler, right? But it's weak limit. So, I mean, you don't, so, okay, you have the compressive compactness, but actually it's not true that you know that you will have for sure solution, and is linked to the vacuum. You can have some cavitation, which makes that those limits may not be a solution. But what we can get is a uniqueness in this set. So now we consider, we forget about actually the Navier-Stokes. We take only inviscid limit of this object, and we have, so this theorem is a theorem with Kong, Moonjin Kong from KAIST in Korea. And so this is Invenciones this year. And basically what we claim, so here is just for shock. We don't know how to do it for BV yet, right? But if you consider S a small shock, and actually I write it above what it means, right? It means that S of Tx is equal to a certain UL for X smaller than sigma T, and another value for X bigger than sigma T. So it is a spatial traveling wave, right? And you take a limit, a sequence of inviscid limits. So you take U epsilon in S inviscid associated to initial value U epsilon 0. I put the epsilon, I said I put epsilon below. Let's try to keep. And it will be U0. Okay, and you have the same thing. If your initial value U0 epsilon converge, I will put strong. If I want really to say how, it will be easier to say if I have the time to explain a bit about the method. So if U epsilon 0 converge to U0, to the S0, the initial value of the shock, then actually the U itself converge, well, weakly we lose things, but that's okay, to the function S, right? When epsilon converge to 0. So this is T equal to 0, this is T positive.
I'm sorry, what is in the equation? Like, what is the M in equation 3? Like on the right side.
This is a viscosity.
Ah, okay.
This is a viscosity, sorry, here. You have 1 over V. Why you have 1 over V is because it's because of the rescaling when you're in Lagrange, right? So if you want the V, so this is the way it is. The mu, actually, if I wanted really to put all the details, my mu can depend on V and has to depend on V. This is a spatial model that Navier-Stokes that we consider. It works with Saint Venant, with shallow water, when actually you have some viscosity which are very particular, right? Okay. So the thing is that actually here, the things that we consider, those U epsilon, right, are not solution of 3. They are limit, inviscid limit of it, right? And what I say is if you take any perturbation of initial value, whatever the things that you take, which came from Navier-Stokes, after a limit, a weak limit, right? Then this thing is stable. You cannot get out from your shock, right? So your shock is stable, not only in terms of weak solution, and now this means that you don't need this additional strong trace things, right? You don't need them anymore. Right? So it's really, so in some way it suggests that being inviscid limit of Navier-Stokes, inviscid limit of Navier-Stokes, right, is better than being a weak solution to the limit equation, right? I mean, I say it suggests because actually I don't know yet how to show that you can actually construct things which out of whack with non-strong trace, right? But it seems that it's better, even if my inviscid limit may not be weak solution, right? But they behave better in this way. What I wanted to say also is that actually the way to show these things
Is your
was,
convergence necessarily weak, or can you upgrade it to strong convergence? Does U epsilon go into S?
the U epsilon, well, it's not clear on why. It's because when you take this limit of U epsilon, right, actually it's because of the vacuum. Actually, your V is the V, which is 1 over rho, right? The V, you have convergence only in measure.
Ah, okay. But at least in some sense, you're not oscillating around it, right?
No, exactly.
So you might have a problem of concentration, but certainly not of oscillation.
Exactly. Well, yeah, but that's a good point for the next, because the next one will have some conditions. But okay, yeah. And so one point maybe that I'd like to mention before going to the next is that actually behind the hood, what we have is we really work on Navier-Stokes, right? And is because what we obtained. I mean, there's two parts. There is one part, and the one part was the stability result on Navier-Stokes on 3, right? But what is important is that uniform with respect to nu. And I think it's the very first result of this kind, right? So this means that you take a level of perturbation of the initial value, right? And we are able to measure how far you will go uniformly with respect to the nu, even for nu converging to 0, right? And this was really, really one of the engine of these things, and it's a result again with Kong, the previous result, which is to appear in GEMS. And that's, yeah, that fuel the result. And so this was a theorem 2. I said that I want to show you a third result, and the third result will be actually multi-D, right? So that's the thing that I think it's also kind of exciting, is that we can begin to say things even in multi-D. But in multi-D, obviously, we need to be very careful of what we claim. Let me keep this. So this is the very first result ever for us in multi-D in this direction, right? And you multi-D, you have really to be very careful, because of course you have all those bad things happening because or thanks to the convex integration, right? Even for very simple shock, right? Convex integration provides infinitely many. So you don't have, I mean, it's the worst case scenario in terms of stability, right? I mean, it's even not non-unique, right? Infinitely many solution with a single shock initial value. So this is a result. So of course, it's due to all the convex integrations, the result by the Lillis and Shekeli differs in compressible, but especially for compressible, I mean, the first result, which was really striking here, was due to Chodaroli, the Lillis, Camillo, and Cremon. And I think it's CPM 13. So when we work with this, we need to remember that we live with those beasts, right? With those things here. So what we were able still to do was considering another kind of singularity. So it's a very, for now, the result for a very specific kind of singularity, which is far better. And for this, to be able to have this kind of singularity, we need to go to the full Euler. So full Euler equation, which means that you have one more equation, right? So maybe just to write it down. So your multi-D, so now I need to write it, so it's dt plus dt rho plus divergence of rho is equal to 0. dt rho u plus divergence of rho u potential u plus gradient. And let me give a the specific model that we consider is an ideal gas. So theta is the temperature, right? And same thing, we'll consider viscosity, which will be evanescence. So this is nu Laplacian u. So the Euler, the Euler is obviously for nu is equal to 0. Here's the Navier-Stokes. So I should have written it. Okay, sorry. Full Navier-Stokes. So here is Navier-Stokes Fourier. But what I'm interested is the limit nu equal to 0, kappa converges to 0. And on top of it, we consider the energy. So let me put energy, total energy plus divergence of u energy plus p, which is rho theta, plus, so here you have or equal kappa Laplacian theta. So this is the Fourier part, right? And plus nu Laplacian of u squared h. Okay, so that's the system, right? And when nu is equal to 0 and kappa equal to 0, this leads to the full Euler system. So it's, I wanted to put it in yellow, kappa n. Okay. And what we will want to do, well, is basically the same thing. So now, well, we have this. Now I will consider a specific singular solution for the full Euler, so at the limits, right? And this is contact discontinuity. This contact discontinuity without shear. So it's a very simple function, but still discontinuous, right? So basically what you can consider it, I mean, is you have, for instance, 2D. I mean, in 3D, we're doing it in 3D, but you can see it as 2D, right? You have the situation x1, x2 here. Here you put a certain value. This will be the UL, right? Which is rho, U, and energy. Here you put the UR. So what are the solutions? So the thing is that actually the UL is a certain rho, no viscosity or no velocity, and I will write with the temperature and temperature L, right? And the UR is also density, no velocity, temperature. And actually, so this means that the velocity are the same, right? The UL is the same than UR. And also the pressure L is the pressure R, which means that you have rho R theta R, which are equal to rho L theta L, but you may have rho R different from rho L, right? So it's a specific solution. It's basically what it means. Why it's stable is because the pressure is the same. At the place you have, you are hotter, right? But you are less dense, right? And there is a compensation such that the pressure is the same. And this is a steady solution. This is a nice steady solution. So on the left you are, and on the right you are. Right? Okay, so what we can claim for this specific solution and the theorem. It's my third theorem. And this with, again, Kong, myself, and Yi Wang. So Yi Wang is in Beijing and is at the Academy of Science in Beijing. So it's an archive here. What we can claim is that, I forget, that's okay. I will define a very weak also family. And what I claim is that, so I should give a name for these things. So I will call it S, right? So S of X equal UL when X1 is negative, UR when X1 is positive. This is my singular solution, right? And I will claim that if now I take a family of initial value, and if the U epsilon lies in a very, again, weak, so it's an inviscid of Navier-Stokes-Fourier. I forget to introduce it, but I will introduce it. Inviscid. So any inviscid weak limit of Navier-Stokes-Fourier, right, with initial value U epsilon 0, and you have the same thing if U epsilon 0 converge in some strong sense to U0, then your U epsilon will converge, and here it will be weakly for sure. You can have, I mean, you can expect some problem here to your S, right? So S. So it's T equal to 0 and T positive. And what is S weak, S inviscid, is as before, is U any inviscid limit. Inviscid limit of Navier-Stokes-Fourier, when the limits are taken kappa first and U second. So you need to take the limit in a certain order. I mean, the kappa has to be very small compared to the U. That's basically it. So again, I don't know, I mean, I cannot say that, so I should put some remarks. So I cannot say that those inviscid limits are weak solution, right? So certainly not in this in this generality, right? I would assume not, but okay. But I can claim that you have a sort of again BV, weak BV, weak BV principle. I mean stability. Stability for S for this singularity. I don't claim for all, right? I mean, but for this one, we have it. So we can say that if your initial value converges to the S, then you cannot go out. So especially it's unique, right? It's unique in the class of inviscid limits. Right? That's okay. So what should I say there? So I mean, I think it's pretty interesting there, because the question, of course, is it unique in the class of weak solution, right? And that's I don't know. And that's actually one. This is one object when you can try to make the you can try to bridge between stability and instability, which is known through convex integration. And in either case, it will be interesting. I mean, if you cannot convex integrate, that's interesting, because it shows that there is a certain object which are stable enough, and you cannot convex integrate. If you can convex integrate, it's also interesting, because it says that, well, when you have objects which are stable enough, there may be some very simple argument, like taking only limit of Navier-Stokes-Fourier, which will avoid, which may avoid the solution. Which doesn't mean that they're not interesting, right? Because there is things which have kind of hidden. The initial value has to converge strongly, right? And this is the only boundary problem that I have. I don't have boundary on things. So in some way, if it is the case, it would be, well, you may still have turbulence, but it has to come from the boundary. Right? That would be another situation. So whatever the situation, I think this is a situation there which is interesting. Even the 1D, I think, because, well, okay, I was supposed to talk about that at the very end, but since I'm a bit late, that's fine. That's even the 1D, more and more, I suspect that you may be able to convex integrate. That's maybe the fact that we have to take out exactly, for the weak limit, exactly the solution, which is telltale of a weak solution, may indicate that actually there is something. But the method that I used for now in order to convex integrate really relies strongly to what is known for the incompressible. And of course here, it's clear that you cannot do this because it's not on the U, right? The velocity is simple here. When you are 1D is also very simple. So it means that if you convex integrate, we have to be with other techniques. And I don't have anything to present here, but it's something that I think we're beginning to have new techniques in this direction and things that we're doing with so convex integration. So we are very close to have a first point in this direction, not the big things that I was hoping for here, but introducing new tools which are really purely incompressible, and something that I'm doing with Chen Yu from University of Florida and Ming Chen. So if I don't have Ming Chen from University of Pittsburgh. So if I don't have time to talk about that later, at least I mentioned that. So I think this is one or another direction when things are interesting, because in some way we are merging with maybe all the interest, right? Not only working on conservation for conservation. Basically, I have 15 minutes, right?
Yes. Can I ask a question before you go on? So what is making the situation of a contact discontinuity much more lucky than a shock, for instance?
Yes, two things. So let me show you very briefly what is the main ideas, the very simple ideas of the old techniques, and then I will be able to tell you exactly what makes these things different here, right? So the main ideas. I could answer your question just by saying, well, because they are more suited to our techniques, right? But it will be easier to say, well, if I explain the techniques a bit first, right? That's basically it. What is the main idea? Well, the main idea, and I can go back actually to the burgers, right? I mean, it's really of the very, and that's what we did with Léger. I don't know if I mentioned it. It was really the first one, the first result in ARMA 11. He was doing this work when he was PhD of mine, and it was really working just on burgers. And the idea, the L2 theory, it is working with relative entropy, right? So it's really coming from the idea of the Fermos and Di Perna. Actually, Di Perna has already a uniqueness result for shocks, not stability, but uniqueness. And it's really going back to this, right? And so when you have relative entropy, what is nice is that like even for a system, you have the same properties that Khrushchev. From one entropy, you can construct infinitely many of them, right? You have this eta of u with respect to another state, v, and you construct this is eta of u minus eta of v minus eta prime of u of v. U minus v, right? So v is constant, right? So it's a function of u, and it gives you a way to see the oscillation of u with respect to this v, right? Because if eta is convex, this behave like u minus v squared. So in some ways, it's like the Khrushchev family, except the Khrushchev is for L1, and L1 is far better for shocks, right? While here is like something which is comparable to L2. And I think that everything was stopped there because as you will see, L2 has a lot of bad property with respect to the shocks. And you can see this pretty quickly. So now, of course, what you want is, and the idea was to work on this. So the relative entropy with, you have the weak strong argument which say that you can still compare to a V which is regular. And then we say, well, let's replace the V by actually a shock. And if you look at what's happening, and I will consider the burgers, right? So let's say the burger. So exactly the solution we were talking just before, right? You put a 1 here, a -1 here. This is a fixed set, and you take a perturbation of that, right? So let me put it, this is this, and just a little perturbation here, right? So it's 1 plus epsilon. And you make it involve. And if you look at what's happening, here at t equal to 0, you have your error, which is over the epsilon in L2, right? So this is the integral of eta of u with respect to the shock dx. Actually, it's like the squared, so it's like epsilon squared. But what's happening is that after a very small time, well, you change the Rankine-Hughes condition. So this means that here, actually, you move from something which is exactly over the epsilon 2 over t. And so this means that the L1 norm, well, is basically the yellow, which becomes the red, is equivalent. But if you talk about L2, well, the height is 1, and the integral is epsilon over 2t. So this means that now, your for t positive, right, your error at time t will be of order epsilon of 2t. So this means that for a fixed t, right, you go from something of epsilon squared to something epsilon. Is very bad. So that's why everything collapses, right? But if you see, as you can see, well, but what is collapse? I mean, the form of the shock, the profile of the shock is fine. It's just the position, right? And actually, it's really this. It's because the position depends really on what happened exactly here, right? So it's very sensitive. The position is very sensitive. But if you move, if you take a shift, if you say, well, depending, which of course depends on the perturbation, right? But you say, okay, I relax it. I say, I don't care where is the thing. I just want to see the profile. Then you have something which is super stable. And then you have even the contraction, right? So it's exactly like the scalar case, I mean, for Khrushchev. If you relax it, you will say, well, there exists a shift, Lipschitz, which depends on the perturbation, right? So very depending, not nice, but okay, depending on you, but such that up to this perturbation, the integral of u tx with respect to s when you take x minus x of t, when you take the shift, these things decrease. Right? So you have a contraction. So this is the idea, right? Is to say that locally your thing looks the same. To go back to your question, Camillo, even there, and I'm not talking about Navier-Stokes, right? Even there, just at the hyperbolic situation, the situation of the shock and the contact discontinuity are different. Because now what you want to do is the same in terms of what we do actually, right? Is the same, is in spirit, we want to move things around, right? So what we move, so I go directly to theorem 3 because it seems, right? So now it's just one point that you move, is everything. So you could say I will try to move the curve, but you know, I mean, it can be really things very, very bad, right? So you don't want to do this. You move really everything. So it's all the xtx. So what you do is you move dtx of tx and you move it to, well, the shift that you need. And it turns out that here, it's one of the good things for these specific things. You know that it is exactly a characteristic. You want to move it at this. So you cannot really do this because your U is not smooth enough, but we do it at the Navier-Stokes level. So in some way, we keep enough, what we say is that when U is positive, we keep enough rigidity of the flow in order to do this. We need slightly more, so we regularize it a bit, right? But basically, this is the idea. You want to move it, right? And when you move it, then you have some property such that you have the same kind of things, at least formally, right? You can say, well, if this was exactly if everything was very smooth, then I will have also a decrease of entropy by moving the things. So this means that, after a while, you can really, well, your things can go maybe like this, but you can also have some ELO. So let's say, this is the left part, right? You can also have some left part like this, because when the nu will be very small, right, you can really have very bad things. But you will say that at least formally, if I put the UL here and the UR here, then formally I control things. I will have my edge entropy go there, right? And why it's okay for my thing is because, if you take a picture of that and you remember what is UL is just hotter and UR cooler with different density to compensate, right? Well, if you put me these very complicated things, it still looks like something which should be preserved. So this means that by moving things, you preserve the profile structure. It's not true anymore if you have a shock. Because if you have a shock, let me do what it means. It means that on UL, you have, for instance, a big velocity here, and on UR, a small one. And it's compensated with density, right? But let's say now that you do the same thing and you move it, right? So you move it. So you have big velocity, small velocity, right? But what's happening is basically what you want to do is to move it along the normal, right? I mean, it's basically the idea. But now if you look at locally here, and let's say that it's flat actually. If you look at locally here, and I'm just looking at locally here, right? Well, this is not a nice profile anymore, because what you have is you have something like this with a big velocity, a small velocity. Well, you don't need pressure here to compensate. So you have some you have some different rule, which is not good. So this means that when you shift your profile, you don't have a good profile anymore. And that's at the level of Euler, the thing which, even not putting diffusion, right, or viscosity. That's what changes things. So in order to go to the system in general to see what you have to do, you have to understand that. And that's what we are trying to do now. But even at the scalar case, you have this problem. So it's really completely different, right? That's and then there's another thing is that actually the Navier-Stokes is good with respect. Navier-Stokes is bad with respect to study of shock, right? Because you have a nice shock, and if you put a Navier-Stokes, then you have a smoothing. So in some way, putting Navier-Stokes smooths out your shock, but it means that you get out of your shock, right? And so all the work going on Navier-Stokes, actually what you have is really to see how this Navier-Stokes and this Euler compensate each other. I mean, how they interact with each other, right? And it has to be very, very subtle. I mean, it is very subtle. Those results of inviscid limits are far more complicated than the one on inviscid, right? I mean, really, really complicated. But here, for this specific case, because the U is equal to 0, so the diffusion with respect to U does not affect your singularity. So there is even something nice with the interaction with the viscous term with respect to the inviscid. Right? So this is those two things which make this case very particular. So it may be that that you cannot do it only because we were lucky with these things. Or we can do with shock, I don't know. That's a new era. And since I have really a few moments, I explained when I was talking about contraction with shift, I didn't say the A. It's because I've cheated actually here. I said that this is true for scalar, and this is true, and that you can do the same for system, and this is not true. This is not true, and there's the last thing that I will say, even at the very beginning, contraction, even in 1D. Contraction with shifts, even with shifts, is wrong for system. And this is something that we proved with Demissaire. It was the Journal of École Polytechnique in, I forgot when, 14, 15, 15, 16, 17, let me put 16, I think. Okay, but what we, no, it should be before, 14, yeah, exactly. Because what we find with Kong was that actually we can do it by weighted. It's okay if you weight the relative entropy. And this is the A. What it means that now what you want to say is that there exists A1, A2, so it's this Kong. When we coin this A contraction with shifts, there is a A1, A2, which depends only on the shock and on the system, such that for any perturbation U, you have that there exists a shift, such that when you take the integral between -infinity to x of t of A1 eta of U with respect to S, shifted. I know it's not shifted because, oh wait, sorry, I want to try to be too fast. Plus integral between x of t, but with A2, so it's constant, A1 and A2 are constant. X of t 2 plus infinity of eta of U with respect to S of tx. So this means here I should have put UL and here UR, sorry. And I will do a picture and I will stop here. This is now decreasing, it works. And what it means that, you know, I count what is on the left and is on the right differently. So this means that you have your things here. You have your shock, UL, UR. You take a perturbation, right? And you count on the left, you count the perturbation in L2, while the difference here weighted with A1, and on the right, the perturbation weighted with A2. And of course, everything is up to a shift. So up to a shift, you can have a perturbation, but you have to count on the left and on the right, and it's something that you need, right? So this means that when you take limit of Navier-Stokes or whatever, if you want it to be true at the end, you need to wait. And that's why we call it a contraction up to a shift, right? That's the whole thing. This means that even in my situation here, I need to wait. And even for this specific situation. Actually, it's interesting because the weight here, you don't have choice. Usually it's a range. Here, the weight is exactly the temperature on the L and the temperature on the right. This is exactly the coefficient A1 and A2. And something that we find even in 1D with Serre. So that was so at the end, you know, even if you want to take a limit, inviscid limit, I mean, you want the things to be to work up to the limit, up to nu equal to 0, kappa equal to 0. So this means that you need to have those weights. If you don't put the weight, the result cannot be true because we know that it's not true at the end, right? So, but if we put the weight, then we have a several situation. So I think I should stop here because I think my time is up. But just, I mean, this is now accelerating. We have a lot of results. There is a lot of things that we want to do. The first thing to show that you have something new is to begin by solving old problems. So we are doing this in 1D. We begin to solve old problem. We are aiming for the Bressan, Bianchini-Bressan conjecture 2004, going from Navier-Stokes to Euler for BV. Basically, we have everything in place, right? I mean, we know how to do it without the diffusion. We know how to do it for one shock. We have to put all those two theories together, theorem 1 and theorem 2. It will take some time because there's a lot of difficulty, but I think that it's possible. There is a whole problem of Matsumura about doing the stability not only of the one shock, but one shock plus a rarefaction. And that's very surprising because you just put one shock, one rarefaction. They know how to do it for a shock, they know how to do it for a rarefaction. In 86, they say, well, we have to put them together. In 92, they said, well, we don't know how to do it. It's an open problem, still open up to now. We have now the right technology to work on the shock, and we are able to do it. This I know we can because we are writing it. This work with Kong and Yi and Wang. This will be out very soon, so that's things. And I think that now, and there's a lot of things to do, and also a lot of new problems that come from these things. And I think also direction which are interesting to try to have tools to be able to go in the other direction than the convex integration in some points, right? I mean, there's at least 2 points when the theory here can be attached, maybe, right? And this is the 1D if we can convex integrate and these things. But of course, convex integration will be very hard because if it is a situation where we can have stability, this means that having the other is complicated. The same way that for us to say anything in terms of stability for shock in multi-D is very difficult because there is a convex integration things. But I think, trying to go in the direction, at least this is points where there is theory when we can say something. And okay, I will stop here.
Thank you. Questions?
So are these A1 and A2 that you have, are they physical quantities? Are they uniquely determined? Or...
Well, it is in this contact discontinuity, and this is the only case. So for the contact discontinuity, the A1 and A2 that you have to put is exactly the temperature of the steady of the discontinuity. So the temperature on the left for the A on the left, the temperature on the right. But this is the only case, and it really depends on the structure of these things. Otherwise, what we had, the first kind of result that we have is that if you fix your shock, if you take A1 and A2 different enough, then it works. So it's basically the work was saying, so I mean, I didn't went into the situation, but you have two family of shocks, the one shock and the two shock, right? And for the one shock, it was to say, well, if A1 over A2 is small enough, then it works. And for two shock is A2 over A1 small enough, it works. And actually one of the big work that we have to do in order to apply it to the BV is because for the BV, you have shocks, you can have a lot of shocks, right? And so small and small and small and small shock. So it was very important to show that actually you can make the A1 over A2 about 1 plus the side of the shock. And actually it was, I mean, it's a huge piece of work which is done by, which has been done by Golding, graduate students, Golding, Krupa, we already former student who's working now with Lady and myself, right? And that's actually, so that's why there is a lot of work still, on the foundation of the theory, because we need, if you want to apply it to more different things, you need a very sophisticated version of it. So actually, Krupa did a lot of work to show that also the X, the shifts, the shift for one shock and shift for two shock are separated. And that's also something very important to say that they cannot mix. So that was another important part of this work. But there, I cannot say really that then it's physical. I mean, I don't know.
Thanks.
Alexis, thank you for a beautiful talk, both in terms of the content and the presentation. The presentation really wows me.
Thank you, Susan.
Maybe one last question. So why do you believe you can do convex integration for the Pernan type solutions?
Did I say that I can? Well, I said that it would be interesting. So I say it would be interesting. And yeah, so I have, but the ideas are really yet rudimentary, right? I know that Shekelidi has the same kind of idea because he's working with a sum. So in some way, in competitions, there will be certainly first. And you'll be fine. I want to know. I don't care if I do it or someone will do it. I really want to know. Maybe not for any system. There is places where it seems that there is some obstruction. But you know, it's just the thing that if you have the basically what you want is to convex integrate P system, right? And the P system, there is no U cross U, right? So this means that your non-linearity is very different, right? But so this means it has nothing to do with the shear flow and the thing. But you have also highly oscillating solution. You have less, but in some way you want to convex integrate less, right? Because it's not a full matrix and so on. So I don't say that I can, but the thing. So what we can do is begging to introduce, but it's the first really level. So what we think we can do is basically going getting the level that is done for incompressible, the fact that you can convex integrate with decrease of energy, finding global solution for all more, for a dense set of initial value for Euler. So you know that it is done, for the incompressible, it's still open for compressible. It's something that people don't know, especially to get the global. And that's the thing. So this is the first level. We still rely a lot on your techniques, but we're begging to put things which are really compressible. So this is the thing that we're doing, that we think that we have. And for the rest is still, you know, it's a plan, right? It's a plan. We'll see. But I think it, you know, and again, for this one is also interesting. This is in terms of 1D model. Because the shock is 1D, right? It's just that you look it in 2D. So you take a 1D shock, you put it in the 2D, and you show that in 2D is unstable. This singularity is also 1D, right? And this is the only 1D singularity for this Euler model, which is that people don't know yet to convex integrate. This is the only one. If you have a shear, then with a shear, it's unstable. I'm not sure it's proof, but I'm sure that it's true. It's also the fact that you don't have any shear, right? So it's the only one. So I think it's, you know, I don't know, maybe it's not possible, maybe it's possible, but I think this is, I'm very excited. I think this, I really would like to have people to, you know, to try it. or help me out. Anything, to know. More than doing it, I really would like to know. This is one point, you know, where things can go together.
Can I ask one last question?
Sure.
Okay. Can you summarize some benefit of like considering this inviscid limit class, or can you work on some other type of weak solution?
Yeah. Well, yes. So why? Yeah. So that's another actually domain of research here, is for which one we can do it, right? And here, there's a lot of things that can be tried, and we're really in the infancy, right? But I can say why we needed the strong trace. Why we needed the strong trace? Because at the end, that's what we want to do, right? Is d over dt of this. And especially you have to differentiate at least this term, right? And here. So actually there's more term again, but just this, you see that you have a sort of x dot eta of u on the left minus eta, especially to ul, u of x of t plus to the right. Right, because it is, you know, it's a differentiation, is eta at the point, but going from the left, minus eta at the right. So this means that you need to have a good limit when to define this quantity, the u along your x of t. Your x of t in time x, right? This is what this is. You have a curve, you don't know what it is, you know that it is Lipschitz, x of t, and you need to be able to take the limit u minus u plus. And that's why we need the trace. It's really at the basic level, right? So what we gain by doing the Navier-Stokes or anything is that you will work on smooth things. So those problems, you won't have it, right? But what you don't have now is that actually the Navier-Stokes work against you, right? All the good things that you have with the hyperbolic, with a real shock, now it smooths out. So it's actually, it works against you, right?
Yeah.
So the idea was to say, okay, well, let's work actually for nu equal 1, Navier-Stokes with 1. And so it's a smooth thing, right? And so now you have UL, right? And it smooths out and you go to UR. And you take and work the same thing at the level of Navier-Stokes. You put a function, a smooth, now it will be smooth, your weight, right? So we have a way to engineer a weight function, right, of these things. And you will put some shift to have the same kind of result at the level of Navier-Stokes. So this means a contraction, the integral of up to a shift of the a function up to a shift. Okay, maybe I say more. You will have to shut me down. Okay, let me add the Tx with respect to your shock, which is now smooth. So you can do all the computation, x shifted, dx, and show that it decreases, right? So this is the same kind of quantity. And if you put nu equal to 0, is basically shifting. And what you do is to show that you can go from nu equal 1 to actually nu by making a change of variable. It's just taking u nu of tx is equal to u of nu t nu x. Right? So it's just squeezing everything, right? And then you are more and more and more steep, right? When you do this and you do a stability argument, usually it fails because when you have a small argument at nu, small initial value, when you scale back, you have a big initial value. So it's not stability. But because we are able to have a contraction, which does not depend on the growth, it's not a stability per se. You can have an initial value which is big, you still have a contraction. Right? And this is why we have something which is uniform with respect to nu. So because we work with this L2, I mean this entropy, because we have a contraction, then we don't care about the strength of the initial value. And because of that, it is enough to work with nu equal 1. And it's basically, we're doing the same things, but at the level of Navier-Stokes.